Now, of course, samples are basically used to estimate population characteristics. For example, the sample mean is, or the mean of the sample is used to estimate the population mean. However, because a sample is a portion or a part of the population, it is unlikely that the sample mean would be exactly equal to the population mean, or the sample standard deviation would be exactly equal to the population standard deviation. Therefore, since the sample mean or the sample standard deviation would not be equal to the population mean or population standard deviation, then we have to expect a kind of a difference between the sample statistics, whether it is the sample mean or the sample standard deviation or the sample proportion, and the population parameter, whether it is the population mean or population standard deviation, and so on and so forth. Therefore, this difference between the sample mean and the sample and the population mean and the sample standard deviation and the population standard deviation, this difference between them is called sampling error. So the difference between the sample statistic and the population parameter is called sampling error. There's a difference between them, because a sample is a portion of the population. So there should always be kind of a difference between the sample statistic and the population parameter. And this difference is called sampling error. So sampling error is the difference between a sample statistic and the population parameter. Now let's give an example to illustrate what we are talking about. Given that Al-Sheikh Car Rental, a company by the name Al-Sheikh, has 5 cars available for rent. This kind of a company, small company, has 5 cars that are available for rent. Listed below is the number of cars rented each day during the week. So during the week, from Monday all the way till Sunday, of course, each day depends how many cars were rented. For instance, on Monday, 3 cars were rented. On Tuesday, 2 cars were rented. On Wednesday, 4 cars were rented. And Thursday also is 4 cars, 4 cars were rented. On Friday, 3 cars were rented. On Saturday, only 1 car was rented. And on Sunday, 5 cars were rented. Great. Now, let's look at these 4 questions based on this problem. The first question, find the mean of the population. Now, as you can see, first of all, we're going to represent the mean of the population by the Greek letter mu, like this. Now, how many rentals during the week? We count them. We just add all of them during the week. This is the population. We have, of course, we sum all of them, okay? We sum all of them, and we divide by 7. We have 7 days. So this is the mean of the population, which is a parameter. We come up with 3.14. So the mean of the population is 3.14. Now, we move to the second question. Select 3 random samples of 3 days. So we're going to select some samples, 3 samples, and each sample consists of 3 days. These are the samples we selected. Sample 1 result in 3 rentals, 3 for 1. Sample 2 in 3 rentals, of course, because each sample consists of 3 days, 3, 1, 5. Sample 3 results in 3 rentals, 3 days, 2, 4, 4. Now, these are the 3 random samples selected. Each sample consists of 3 days or 3 rentals. Calculate the mean of each sample. This is the mean. The mean of sample 1, we just add all of those, 3, 4, 3. We add 3, 4, and 1, and divide by 3. We come up with 2.67. The mean of sample 2, we just do the same thing. We just add the 3 ones here. 3 plus 1 plus 5 over 3. The mean of sample 3, we do the same thing. We just sum those rentals and we divide by 3. We come up with 3.3. Great. Now, notice the following. We're talking about compare here. Talking about calculate the mean of each sample and compare it to the population mean. As you can see, the mean of the sample 1 is 2.67. It is less than the population mean. The second sample has a mean of 3, which is still less than the mean of the population. The third sample has a mean of 3.3. It is greater than the mean of the population. This is a comparison between the sample mean and the population mean. Great. Now, remember that we have a population of 7 values. Population of 7 values. And samples each of 3 values. The total number of possible samples is calculated using the combination formula. Okay? Which is, as you can see, this is the formula where n is 7 and r is 3. So we come up with how many samples? 35 possible samples. So out of this, we're going to have 35 possible samples. We can select 35 possible samples using the combination formula. If n equals 7 and, r equals 3, because each sample consists of 3. Now, part 4, what is the sampling error in each case? The sampling error. We already said the sampling error is the difference between the sample statistic and the population parameter. So, in sample 1, sampling error is, x1 bar, of course, minus mu, which is equal, the difference is minus 0.43. Okay? 47. Sample 2, the sampling error is x2 bar minus mu, 3 minus 3.14. We come up with minus 0.14. Sample 3, sampling error is, the sample mean of sample 3, of course, minus the mu, which is the population mean. We come up with 3.3 minus 3.14, and we come up with 0.16. So notice that each of these differences, which is minus 0.47, minus 0.14, and 0.16, is the sampling error in estimating the population mean. Now, of course, we have discovered that there is a sampling error, or there's a difference between the sample statistic and the population parameter. So, if there is a possibility of a sampling error, that is a difference between the sample statistic and the population parameter, how can polling organizations and other organizations, such as ABC News, make an accurate prediction about, say, a presidential race based on, let's say, 2,000, a sample of 2,000 registered voters out of, say, 90 million or 100 million, voting population. So to answer this question and other questions, other related questions, we first develop a sampling distribution of the sample mean. Therefore, organizing the means of all possible samples into a probability distribution will, of course, give us the sampling distribution of the sample mean. So when you organize all the means of all different samples, of course, into a probability distribution, you will come up with the sampling distribution of the sample mean. So to illustrate what we are talking about here, let us give this example and see exactly how these concepts are illustrated. The example, say Cairo Industries has 6 employees, 6 production employees or workers. Consider the population. So those 6 production workers, are considered the population. The hourly earnings of each employee are given below. So you have the employees and their names: Ahmad, Walid, Omar, Salwa, Rami, and Hassan. Hourly earnings, you get $55, $4, $6, $7, $7, and $8. These are the earnings or wages of those 6 employees, each employee, of course. Now, the question, we have 4 questions in this problem. What is the population mean? What is the sampling distribution of the sample mean for samples of size 2? Each sample consists of 2 items. What is the mean of the sampling distribution? What observations can be made about the population and the sampling distributions? First of all, part 1, question number 1. What is this population mean? So the population mean, we used to designate the population mean with the Greek letter mu. Is used to, stand for the population mean. So it's written like this. So the population mean, mu, is equal summation of all the earning, and here we're talking about, of course, all the earnings of the employees over the total number of employees. So we come up 5 plus 4 plus 6 plus 7 plus 7 plus 8 over 6. We come up with $6.16. This is, of course, the mean of the population. Now, the second question, what is the sampling distribution of the sample mean for samples of size 2? So, to arrive at the sample distribution of the sample mean, we need to select all possible samples of size 2 without replacement. So we have to use the combination formula. So the combination formula, of course, is stated here. C stands for combination, so you get N, which is the number of this is the total number of items in the population, and then 2 is the total number of items in each sample. Okay, so combination 6 and R. Okay, and this is the formula: 6 factorial over 2 factorial into N. 6 minus 2 factorial, and we can simplify this, and we come up with 15, different possible samples. So out of this population of 6 employees, we're going to, select, or we're going to construct 15 different samples of size 2. Now, let us see how we can do that. So you get the sample, the employees here. So we're going to start. We're going to have 15 different samples, 1 all the way till 15. Now, we get here, 4 heading: sample, employees, earning, sum, and mean. We get 5 headings, 5 heading. And then sample, employee, earning, sum, and mean. So, sample 1, okay, is what? Ahmad, Walid. I represent those by their first letter, capital. Ahmad by, we're going to represent this Ahmad by A. It's first, letter of Ahmad. So, Ahmad W, Ahmad A W. Then we move A Omar, A O, then AS, AR, AH, as you can see. Now, we move. We finish from Ahmad, we move to the next employee, Walid. So the Walid, we construct now a different sample. Walid Omar, WO. Walid Salwa, WS. Walid Rami, WR. Walid Hassan, WH. As you can see over here. Now we move to the 10th sample. Okay? Umar Salwa, OS. Umar Rami, OR. Umar Hassan, OH. We finish from Umar, okay? Now we move to Salwa. Salwa Rami, SR. Salwa Hassan, SH. As you can see here, SH. Then we finish from Salwa, we move to Rami. Rami Hassan, RH. And you see RH. Now we move to the third headings, earnings. Now we know Ahmad earned $5, Walid $4. So we get 5, 4. Ahmad Omar 5, 6. 5, 6. And so on and so forth, so on and so forth. Umar Salwa, Umar earned how much? 6, Salwa earned 7. So we get 6, 7. We finish from that. We move to the fourth headings or fourth column, sum. Okay, we sum this 5 plus 4, we get 9. 5 plus 6, you get 11, and so on and so forth. You add them. You add all this. 6 plus 7, 13. 6 plus 7, 13. 7 plus 8, 15, and you come up with sum. Now we move to the last column, which is, under the heading of the mean. The mean is the sum over the total number. So we get, the sum is what? 9 over total number 2. So 9 over 2, we get 4.5. 5 plus 6, 11 over 2, we get 5.5. Okay? And then we sum all of them. Okay? You get 12 over 2, 6, 12 over 2, 6. And you get the mean. Over here, the same thing. This is the sum. And you divide by 2, you get 6.5. 15 over 2, 7.5. We get, the means. Now notice that all 15 sample means are used to construct a probability distribution as stated below. Now how can we construct the probability distribution? Now we know the means. We have already calculated the means, the sample means. Of course, now let us construct the, the probability distribution out of these sample means. Now we get sample mean 4.5. How many 4.5 do we have over here? 4.5. We get 1. Only 1. So we have 1 4.5 out of those 15 means. So we put 1. Now, how about 5? How many 5 we have here? 5, we get 1. We only get 1. How many 5.5 do we have? 5.5, we have 1, 2, and 3. We get 3. Okay, 5.5, we have 3. Great, we have 3. Okay, we have 3. Now, what about 6? 6, we get 1, 2, 3. We get 3. What about 6.5? 6.5, we get 3 also. 6.5, 1, 2, and 3. We get 3. What about 7? 7, we get what? We get 1, 2. What about 7.5? Also we get 2. Total number is 15, as you can see. What about the probability? So the probability we have 15, the total number, and we have 1, 4.5. So the probability of it is that 1 over 15, we get 0.067, or 6.7%. The same thing, 1, 5, the probability is 1 over 15, we come up with 0.067. 3 over 15, we come up with 0.2. 3 over 15, we get 0.2. What about 3 also? We get 0.2. Okay? Okay? Now, what about 2? 2 over 15, we come up with 0.13. 2 over 15, we get 0.13. So if we sum all of those, the probabilities, you have to come up with 100% or about 1. So we come up with 1. This is the total number of probability. So the sum of probabilities is equal 1, of course. Now, part 3, this is, as we said over here, therefore organizing the means of all possible samples into a probability distribution will give us the sampling distribution of the sample mean. So this is the sampling distribution of the sample mean. When we construct or organize the means into probability distribution, then we come up with of course, the sampling distribution of the sample means. Now, question number 3, what is the mean of the sampling distribution? Of course, the mean of the sampling distribution is usually written mu x bar. Mu x bar. Mu x bar. Okay? So, the mu x bar is the sum of all sample means over total number of samples. Now, all sample means, as you can see, these are the means, you get 15 ones. Sample means you get 15 ones. So what you do, we add them, all of them, 4.5 plus 5.5 plus 6 plus 6 plus all of those things, plus 5, 6.5 plus 5 plus 5.5 plus 5.5 plus 6 plus 6.5 plus 6.5 plus 7 plus 7 plus 7.5 plus 7.5. So we just shorthand this one here, and we come up with, sum of all of them and divide by 15. We come up with 92.5 or 15, and we come up of course, the mean of the sample distribution is 6.16. So mu x bar is 6.16. Now we have the last part or last question, of this problem. We will solve it right away once we erase the board and solve the last question. Now we continue the problem. We ended at part 3 of the problem, question number 3. Now we move to question number 4. What observations can be made about the population and the sample distributions? Of course, to do that, as you can see, this is the solution of course, problem, question number 4 over here. Okay? Now, as you can see, below are the population distributions and the distribution of the sample means. This is here the distribution of the population. So we have the hourly earnings along the horizontal axis, and then we have along the vertical axis the probabilities. Okay, as you can see, this is the population. Okay, how many persons or employees earn $5? Only one. 1 out of 6. So 1 out of 6 is how much? We have 6 individuals. So 1 out of 6, we come up with what? Of course, 0.16. Okay, so 1 out of 6 is 0.16. Okay, now, same thing for how many persons or individuals earn $4? Is only 1. 1 out of 6 is 0.16. Now, with the same thing, 6. We have only 1 person earns $6. 1 out of 6, we come up with the probability. So the probability is going to be 0.16. Now, how about 7? We have 2 persons earning 7. Okay? 2 persons earn Salwa and Rami earn $7. So 2 out of 6. 2 out of 6 is 0.33. Okay? 8 is 1. Okay? 8 is 1. 1 out of 6 is going to be 0.16. So when we draw the distribution of the population, of course, 4 we got in probability 0.16, 5 0.16, 6 0.16, as you can see, 7 0.33, 8 0.16. So this is the probability along the vertical axis, and here the hourly earnings. As you can see, hourly earnings. So this is the distribution. What about the distribution of the sample means? As you see, these over here we have how many means is 4.5. Of course, we have one that has 4.5 as a mean. Okay, how about 5? We have only one. Okay, so 1 out of how much? 2, 4, 6, 7. 1 out of 7, 0.067. 0.067. So 4.5 and 5, we get 1. The probability of getting 4.5 is 0.067. The probability of getting 5 is also 0.67. Okay? Now, how about 5.5? We get what? 3 means with 5.5. So 3 out of how much? Of course, 3 out of 15. Okay? So we divide 1 out of 15, 1 out of 15, 3 out of 15, 3 out of 15. So here you get 3 numbers. We have, let's see, 5.5, 3 samples that have 5.5 as means, 3 samples that has 6, as a mean, 3 samples that have 6.5 as mean. So if we divide 3 over 15, we come up what? 0.13. Okay? We get, of course, 0.2. Sorry. So 3 out of 15, 0.2. Okay? Therefore, 5.5 and 6 and 6.5, they can have probability of how much? 0.2. Okay? 0.2. As you can see, 5.5, 6, 6.5, they have probability of 0.2. Now we move to 7. 7, of course, we have the probability is 2 values or 2 samples have, mean of 7. Therefore, the probability is 0.13. As you can see, 0.13, of course. The same thing, 7.5, we have 2. The probability is 0.13. So this is the shape of the population distribution as well as the, the sample means. Now, we can conclude certain observation out of the, these drawings. Okay, the following observations can be made. The first thing, as you notice from the solution of the problem, the mean of the distribution of the sample mean is 6.16 over here. And the mean of the population is 6.16. It's over here. So this is the mean of the population that we have already calculated at the beginning of the question, the problem. It's 6.16, which is the same as the mean of the sample, of course, mean. 6.6, they are equal. Now, the spread in the distribution of the sample mean is less than the spread in the population values. Okay? As you can see, the mean over here, the sample mean ranges from 4.5 to 7.5. It has a narrower spread than the population values, than the population distribution. As you can see, the spread in the sample mean ranges from 4.5 to 7.5. So the spread is, subtract 7.5, the highest minus the lowest, we come up with 3. Now, what about the population? The spread in the population. It ranges from 4 to 8. So here we get the spread is larger in the population values than the sample means. Here the spread is 4, however the spread here is of course 3. So the spread in the sample mean is less than the spread in the population. And the third observation we can make is that the distribution of the sample mean tends to be more bell-shaped, as you can see over here. this is kind of more bell-shaped, okay? And it approximates the normal probability distribution. Over, if you look over here, you know, it's nothing you can see here. It's not a bell-shaped. So the distribution or the shape of the sample means, of course, tends to be bell-shaped, tends to be close to a bell shape, and that tends to approximate the normal distribution, while the distribution of the population is not at all look like a bell-shaped type of distribution. Okay, so these are the observations we can make, three main observations we make out of this question. Okay, now we have another example. Let's say example 2 here. Or actually example 3 here. A population consists of the following 5 values: 12, 12, 14, 15, 20. Okay, this is the population. Now, question number 1, list all samples of size 3 and compute the mean of each sample. B, compute the mean of the distribution of sample means and the population mean. Compare the two values. C, compare the dispersion or spread in the population with that of the sample means. Okay, now, A, solution, how many samples of size 3 do we have? Of course, use the combination formula. This is the combination formula. We're going to come, of course, with 10 samples. Okay? Now, of course, these are the samples. We're going to have 10 samples, as you can see, number 1 or 10. Now, each sample consists of 3 items, okay? So we count 12, 12, 14, okay? 12, 12, 14, 12, 12, 15, 12, 12, 20, and so on. 12, 14, 15, 12, 14, 20, 14, 15, 20, 12, 14, 15, 12, 15, 20, 12, 14, 20, 12, 15, 20. Okay? These are the different, possible samples, okay, that can be obtained from this population of 5 items. Samples, each of size 3. Now, the sum, of course, if we sum all the values, each sample consists of 3 values. So we sum them, become 38. It means 38 over 3 become 12.66. The sum of this is 39. 39 over 3 become 13, and so on and so forth. You just sum them to get the mean, sum them and divide by 3, and we come up with all these means. Okay, now, part B, compute the mean of the distribution of the sample means. Of course, we already designated the mean of the sample means by sigma mu x bar, which is equal the sum of all these means. Sum of all these means. So 12.66 plus 13 plus 14.6 all the way plus 15.66, and we divide by 10 because we have 10 here, 10 samples, and we come up with what? 14.6. And the population mean, we just add all those and divide by 5. Of course, we come up with, of course, 14.6. Okay, now, compare the dispersion in the population with that of the sample means. As you can see, the dispersion, of course, can be calculated or computed by using the spread. The spread, of course, is the difference between the highest value and the maximum value and the minimum value. So if we want to get the spread in the population, all we have to do is subtract 12 from 20. So we come up with 8. If we want to compute the spread in the sample means, of course, we'll get here, subtract the smallest from the largest. The smallest is, 13, of course, 12.66, okay, is subtracted from 16.33. So 16.33 minus 12.66 will come up with 3.67. So as you see, the dispersion in the sample means is much lower than the dispersion in the population values. Therefore, the dispersion of the population is greater than the dispersion in the sample means. Okay, now we move to talk about the central limit theorem, which is a very important, theorem. It says that if all samples of a certain size are selected from any population, whether the distribution of the population is normal or non-normal, skewed positively or whatever, okay? Then the sample distribution of the sample mean is approximately a normal distribution. This approximation improves with larger samples. Here is what actually the central limit theorem says is that no matter of the shape of the population distribution, when you sample from that population, okay, then you're gonna have a distribution that has a different shape than the population. And the shape of the sample distribution will converge to a normal distribution when the number of observations in each sample increases. Okay? The example presented in the chapter, of course, the example consists of 40 items in the population, and of course, the distribution of the population was almost positively skewed. Now, when we sample, from that population, samples of size 5, we sample about 25 samples of size 5. That is, each sample consists of 5 items. The distribution of, the sample means was different. The shape of that distribution was different than the population distribution. When the sample, of course, items or the sample size increases from 5 to 20, then the distribution of the sample means has converged to a normal distribution. So this is the essence of the central limit theorem. Okay? So he's saying the approximation improves with larger samples. That is, the approximation of the distribution will become normal distribution with larger samples. That is, when samples, has larger items. Instead of 5 items, you have 15 items. Or instead of 15, you have 20 or more. Then when the sample size increases, that is, it consists more items, then we expect the distribution of the sampling distribution of the means to converge to a normal distribution. So this theorem shows the following important points. Okay, the conclusion of that theorem is that regardless of the shape of the population, no matter what the population shape looks like, the sampling distribution of the sample mean will move toward the normal probability distribution, of course, will move toward the normal probability distribution. No matter what the shape of the population, however, the shape of the sampling distribution of the sample means will, converge to a normal shape. The larger the number of observations in each sample, the stronger the convergence. That is, the convergence to a normal distribution will be, of course, stronger the larger the number of observations in each sample. That is, instead of 5 items or 5 observations, you have 10 or 15. The more items you have in each sample, then the stronger the convergence to a normal distribution. Also, we can conclude, even though these 0.3 and 4 and 5 are not part of the central limit here. However, we can say the following: that there is less dispersion in the sample distribution of the sample means than in the population distribution. That is, the dispersion which is computed by the spread, of course, in the population. The spread in the population is larger than the spread in the sample means. That is, the dispersion in the sample distribution is lower than the dispersion in the population. The mean of the sample means is close to the mean of the population, to the mean of the population. It can be demonstrated that the mean of the sample distribution is the population mean. That is, mu of x bar is equal to mu. Mu is the population mean, and this is the sampling, of course, the sampling mean. Okay, and if the standard deviation in the population is in sigma, the standard deviation of the sample means is sigma over radical n, where n is the sample size, where n is the size of the sample. Therefore, a standard error of the mean is equal sigma of x bar is equal sigma over radical n. This is the standard error of the mean. Now, let's talk about this example here. A certain company has 20 sales representatives who sells its product throughout the country. Okay, they sell the product of that company throughout the country. The number of units sold by each representative last month is listed below. Okay, you have 20 employees, sales representative. Now, last month, the number of items, units sold by each employee is listed here. So the first employee sold 2 units, the second employee sold 3 units, and so on and so forth. The 20th employee sold 5 units, okay? Assume that these figures represent the population values. So we have here 20 population values, okay? Draw a graph showing the population distribution. This is the graph here, okay? Let's, read the question first and then move to the solutions. Compute the mean of the population. C, select 5 random samples of 5 each. Compute the mean of each sample. Compare the mean of the sample distribution of the sample means to the population mean. Would you expect the 2 values to be about the same? First, E, draw a histogram of the sample means. Do you notice a difference in the shape of the distribution of the sample means compared to the shape of the population distribution? Now, A, draw a graph showing the population distribution. This is the graph over here. Of course, here we have the, the observation in the population, of course, and we have the probability. Of course, you get 2, we get how many items? 2, 1, 2, 3, 4, 5. So we get 5 items. Of course, 2, you're going to have the probability is, as you can see, 0.25. Okay, and the probability of 3 units, of course, 3 number of units, number of units sold. Okay, and you get, these kind of the distribution. Okay, this is the distribution of the population. Now, of course, we have already talked about questions like these in previous problems. Okay, along the vertical axis we have the probability, and along the horizontal axis we have the number of units sold. Now, we compute the mean of the population. This is the mean. We sum all of those number sold, okay, over 20, okay, and we come up with 3.3. This is the mean of the population. C, select 5 random samples of 5 each. This is the sample. You have 5 samples. Remember that, of course, we're going to have, if we calculate how many samples we can obtain out of these 20, okay, the population 20, and the, of samples of size 5, okay? So we're going to have many samples, of course. You're going to have over 1,000 samples, of course, when you use the combination formula to calculate how many samples we can obtain out of these 20 numbers. Okay, 20 values. This is the population of, of how many samples we can get if each sample consists of 5 items. Of course, we're going to use the combination formula, which is C25, okay, which is actually C25, which is equal, of course, 20 factorial over 5 factorial over 15 factorial. If you calculate this one, you're going to have a large number, of course. Here we're going to choose only 5, samples. Of course, these are the 5 samples, and these are the sampling data: 23233, 32334, 23342, 33424, 32273. Okay? And the sample means, as you can see, we just added all these and divide by 5. We added all these, divide by 5. Same thing we do for all those, and we come up with the sample means. Of course, D is what? Compare the mean of the sample distribution, of the sample mean. This is the mean of the sample distribution of the sample means. Of course, mu of x bar, which is the sum of all sample means. We just add all of those, and we divide by the total number of samples. We get 5, and we come up with 3. Okay, we just add all of those and divide by the total number of samples. Of course, you're going to come up with, of course, 3. Okay, now you notice that the population mean is kind of greater than the sampling, the mean of the sampling distribution. Okay, we have here 3.3 and here about 3. Okay, with other samples, you will expect, to be close to each other. You're going to have many thousand samples, so I'm very sure with other samples you can have, the values are close to each other. Now, E, say draw a histogram of the sample means, do you notice a difference in the shape of the distribution of this sample means compared to the shape of the population? If you look at the distribution of the population, you know, it's like here, it's good, positive skew. Something like this here. It's like positively skewed, you know? Like it, but however here, you know, we get the sample means, number of means, you get 1, okay? And the probability 0.2 over 0.2. So as you can see, the distribution of the sample means is different than the distribution of the population. Okay? So remember that when we, of course, increase the size of the samples, you know, if we get, you know, for instance, sampling of 15 samples with larger size number of each sample, we might, you know, of course, we might expect the sample distribution of the means to converge to a normal distribution, to become close to a normal distribution. Okay? When you increase the size of each sample, of course, you're going to expect, you know, the center limit, the center limit works. So you're going to expect this distribution of the sampling means to look like the normal distribution. So the larger the size of each sample, of course, the stronger the convergence to a normal distribution.